The second speaker is from Austria, from the University of Innsbruck. Andreas Pinter is going to talk about SPARE, Shortest Path Global Item Relations for Efficient Session-Based Recommendation.
All right, so hello and welcome everybody to our presentation of the paper SPARE, Shortest Path Global Item Relations for Efficient Session-Based Recommendation. I'm Andreas Pinter and this work is a joint work with Amir Reza Mohammadi and Eva Zangalev from the University of Innsbruck. So to start with, I want to shortly introduce the concept of sequential recommendation as well as session-based recommendation. So in sequential recommendation, we emphasize the dynamic in the user interaction sequence and explicitly model the sequential context. However, due to data privacy regulations or other factors, it can happen that no user information is available and the user sessions are completely anonymous. And this leads us to the task of session-based recommendation. So in a session-based recommendation system, we aim to predict the next item the user will interact with only based on the preceding interactions in the current session, without any additional information about the user. So current state-of-the-art models for session-based recommendation model the sequential item-to-item relations in a graph, and they use graph neural networks or short GNNs to learn useful item representations for computing the final recommendations. However, there are some downsides to this approach. First of all, GNNs are sensitive to noisy data, which can lead to deceptive item representations and therefore worsen the recommendation performance. Also, GNNs cannot capture long-range dependencies since they are limited by the receptive field of each node per layer, which means they're one-hop neighbors. Stacking multiple graph neural network layers enables them to capture multi-hop relations, but it introduces the problem of oversmoothing, where the node representations converge to the same values. The problem of oversmoothing usually happens if the number of GNN layers is larger than 3. However, in real-world datasets, it's very common that sessions contain more than 3 item interactions, and items separated over longer distances can hold valuable information. To make these aforementioned issues more clear, we provided some template sessions of an e-commerce grocery retailer, and the numbers here indicate the occurrences of the sessions in a synthesized dataset. So there are some frequently occurring sessions that include ingredients of a pizza recipe, for instance in this case sessions 2 and 4. Also there are some less common ingredients under those pizza ingredients such as pineapple in sessions 1 and 5. Also, there can be customers who may buy unrelated items such as shampoo or chocolate in a session, for instance in session 3 and 6. So the purchase of shampoo or chocolate seems like an irrelevant outlier to a customer who is looking for pizza ingredients. But pineapple can be considered as an interesting pattern here. To utilize these insights, we propose to model the item relations in a graph via shortest path search, which introduces shortcut connections and also graph edge sparsification. For this example, this means through the high support of pineapple to dough and dough to tomato relations, a shortest path search in a global item graph finds a direct connection between pineapple and tomato. Furthermore, since item relations containing shampoo or chocolate have a low support, the shortest path search disregards them as irrelevant if we give a proper threshold value for the shortest path search. So here we can see the graph construction phase of our model, which we name SPARE for shortest path relations. So from the user input sessions, we built a global item graph with weighted edges between the items. The weights correspond to the frequency of the consecutive appearances of both items across all the sessions. And in a second step, we perform a shortest path search, which on the one hand introduces the shortcut connections between the items which is indicated by the red arrow. And this solves the oversmoothing issue of GNNs. On the other hand, it filters unreliable item-to-item relations above a cost threshold, which is related to the edge weight. And therefore, it introduces graph edge sparsification, as shown by the missing edge in the final graph. Both of these augmentations of the graph also impact the training efficiency, since the item-to-item graph has a higher degree of sparsity, and we do not need multiple layers to get information from far away neighbors. However, this graph edge sparsification comes with the risk of increasing the data sparsity and the popularity bias. And to counteract these problems, we apply supervised contrastive learning, or short SCL, by extracting positive and hard negative item samples in a data-driven manner. So the selection of hard negative item samples is crucial to truly contribute to the gradient of the optimization. With supervised contrastive learning, we not only tackle the sparsity of the data, but also improve the model's performance by refining the encoder and the item representations through the self-supervised learning objective. For extracting the data-driven positive item samples, we define positive sessions as sessions in the training data with the same target item as the input session. And due to the assumption that in session-based scenarios, the last clicked item in a session is the most important to the target item, we use the last item in each of the positive sessions and the target item of the input session as positive samples for our contrastive learning objective. To find hard negative items, we sample all sessions containing one or more items from the input sessions, and excluding the sessions with the same target item. And these negative candidate sessions are refined by borrowing a metric from the NLP domain. So to the best of our knowledge, we are the first to use the Bleu score for session similarity computation. The Bleu score consists of counting the number of matching n-grams of items between the reference sessions, so the input and positive sessions, and each of the negative session candidates. Then the candidate counts are summed up and normalized for the final Bleu score. The last item of the negative sessions with the highest Bleu score are used as negative items. With this technique, we are able to distill very hard negative items as hard negative samples for the contrastive learning objective. Here we can see a complete overview of the whole approach of our model. So first, the global base item graph is enriched by shortest path connections in the graph during the construction phase, and it also drops low support edges. The resulting graph is then input to our recommendation component, particularly to our graph convolutional layer and a soft attention component to learn the corresponding session representations. These session representations are then enhanced by the supervised contrastive learning task, which relies on the already described session sampling procedure. From the final session embedding, we can compute the prediction scores of each item in the candidate set. To evaluate the performance of our approach, we conduct experiments on 3 widely used and representative data sets from the e-commerce as well as from the music domain. So Tmall and Retail Rocket contain user logs of online shopping platforms, whereas Last.fm includes music listening histories. We compare SPARE with several representative baseline and state-of-the-art methods. In terms of state-of-the-art methods, we have GCE-GNN, which employs a global as well as session graphs for item representation learning. S2, DHCN, and Kotrek both introduce graph-based contrastive learning methods, and recently MGIR proposes to model the sequential as well as the negative relations of items via graphs. We use precision and MRR with cutoffs at 10 and 20 as the evaluation metrics. So, our proposed method SPARE significantly surpasses all current state-of-the-art baselines methods on the 3 datasets on all provided metrics. Especially on Tmall, we were able to improve the state-of-the-art by at least 7.8 percentage points on all metrics. Additionally, we observed that CODREC and MGIR have competitive performance on the Retail Rocket and the Last.fm datasets. However, both of these methods introduce a complex architecture and have a higher running time compared to our model SPARE, which limits their practical applicability, which we will have a look in a later slide. To investigate the impact of each component in our approach, we present different variants of SPARE: SPARE Base, SPARE NSP, and SPARE NSCL. In SPARE Base, we omit the shortest path search as well as the supervised contrastive learning. For SPARE NSP, only the shortest path search on the global item graph is removed. And for SPARE NSCL, only the supervised contrastive learning component is discarded. On both datasets, the shortest path search and the supervised contrastive learning are able to improve their performance significantly if applied separately. Still, the integration of both components leads to the best performing models on all metrics, showing that the supervised contrastive learning complements the sparse shortest path graph representation learning. Also, we introduced BLEU as a measure for session similarity. And to justify this design choice of measure and to display the impact of the supervised contrastive learning component in our model, we compare different session similarity measures. So nearest neighbor-based methods for session-based recommendation usually rely on session similarity measures to filter out relevant sessions for the computation of the potential next item candidates. So following their intuition of defining sessions as a set of items, we include the cosine similarity for sets and a Jacquard index as set-based similarity measures. Additionally, we also include the Levenstein distance, which is usually used to measure the edit distance between two sequences in our comparison. So as shown here, most of the different session similarity measures are able to improve the performance of the base model without the supervised contrastive learning. Interestingly, the set-based measures perform better than the more sequence-oriented Levenstein distance. Nevertheless, our used BLEU metric with its ngrap overlap-dependent measurement outperforms all other session similarity measures and shows the importance of considering the sequential dependencies of sessions. Due to the graph edge sparsification and the shortcut connections, SPARE can efficiently model item relations. We compare the running times per epoch as a proxy for efficiency against the state-of-the-art graph-based methods for session-based recommendation. Our approach has the fastest running time on the DMOL dataset as well as the Retail Rocket dataset. And if compared to the second best performing model in terms of precision and MRR on the Last.fm dataset, which is MGIR, our model SPARE is faster by a factor of 1.5 in training. And this clearly indicates that our approach learns the global item representations very efficiently compared to the other state-of-the-art graph-based methods. Previously, we also introduced the assumption that SPARE, through its shortest path shortcut connections, inherently introduces a large receptive field per node. Consequently, SPARE does not have to rely on multiple layers to aggregate the node information from neighbors that are multiple hops away. And to confirm this intuition, we compare SPARE NSCL, so our model without the supervised contrastive learning component, and CODREC, the model showing the second best overall performance, with a different number of layer settings, since both of them use a very similar graph convolutional operation. We can observe that CODREC heavily relies on learning the item representations in the graph by using the information from n-hop neighbors. And it constantly reaches its best performance in the 3-layer setting, but it clearly oversmooths with a higher number of layers. In contrast, our proposed method SPARE has a stable performance across all settings of layers, indicating that the multi-hop connections are effectively captured by shortest path shortcut connections. So, to conclude, in this paper we propose a novel session-based recommendation model which relies on a shortest path search to filter out unreliable relations and also to introduce shortcut connections to items that are multiple hops away to tackle the oversmoothing issue. Moreover, we present a novel supervised contrastive learning method based on a data-driven positive and negative item samples for session-based recommendation. And to find hard negative samples, we propose to use the Bleu metric to find similar sessions to the reference sessions. And the results show that our approach has state-of-the-art performance on 3 data sets and is more efficient than other baseline methods. You can find the corresponding code on GitHub, and thank you very much for your attention.
Thank you. We have time for a couple of questions. Is there a question in the audience? There is a question online, however. So in your presentation, you make a distinction between sequential and session-based scenarios. What implication does it have on model selection, and why can't we use the same models?
So in a session-based scenario, it's more likely that sessions have less interactions, and since you're missing the user information from long interaction sequences, you need some additional information introduced in the model to perform good recommendations. So I think this approach is more likely to be used in session-based recommendation than in sequential recommendation approaches.
Okay, and in your presentation, you mentioned that your system, right, outperforms all the baselines significantly, and you provided the p-value. But did you correct for the multiple comparisons to baselines? Was the test corrected? What statistical test you used, and was it corrected? Yeah, there.
Like we used a standard student pairwise statistical test to check the p-value if it's like in the range, and corresponding to the p-value it was fine.
Yeah, but you have multiple baselines, so you should correct for the fact that you are comparing to multiple baselines, not a single baseline. So you need to correct for the t-test.
I think for this we always use the second best performing model as a comparison.
So you're comparing
Yeah.
only to one system.
Exactly, yeah.
Okay. Any other questions? Okay, let's thank the speaker then.